now talked about absorption, reflection, refraction, now diffraction. Diffraction is another very, very crucial phenomena to understand, because by this concept or by capitalizing this phenomena, we have started to form images. So how an image is being formed, and how we can capitalize this phenomena of diffraction to get our image of interest is what we are going to see here. So first is, if you can see this example, this particular example, just think this is a reservoir or of water, and this reservoir, this is one gate which is open at present. You can see this animation, this is open. Now, if we close this, you see the reservoir water is still and there is no water flowing outside, right? Now, when this gate is opened, what we expect is this flow is linear. You can see here, this water inside the reservoir is linearly flowing. So it is parallelly waves, you can see here. And when this same water is allowed to pass through a small slit or a small opening, what happens, you can see there are circles being formed. Instead of having a linear waves, so it is becoming circular waves, and these waves are progressing in the circular manner. So precisely, you see this barrier with a narrow slit at this position, and when this is open, you see these circles or angular rings. Angular rings are being formed. This circles or this wavelength propagation is something which is very interesting, because based on this, we have to see how the property of light interacts. So to start with, Thomas Young was the scientist who first, in a way, challenged Newton's theory or idea of light being a particle in nature. So that time Newton had already come up with this corpuscular theory. So Young was the person, he was a young man, basically, a young scientist, and he did an experiment. And with his experiment, he tried to prove that so you can see here the experiment designed by Thomas Young. So what he said, what he did is his experiment, you can see the diagram here. This is first the single slit when this light was coming, and through this single slit you can see the the wave pattern here, and these are diffracted coherent spherical wave fronts. I can see here the crest and the trough basically. And when the same wave fronts are again forced to pass through two closely spaced slits, narrow slits, then there has been like interactions or between the diffracted coherent spherical wave fronts. And so two sets of spherical wave fronts created, and they interacted with each other. So the line of waves out of step, you can see here in the red as well as in the black. So where both the wave fronts, spherical wave fronts, they matched or they sync with each other. So they are in step with each other. They are has been with the red color, and where they are out of step, they are out of sync. They are in the in the black arrow has been depicted here. Now, based on this alternate red, black, red arrows, what we get is a pattern of bright fringe alternated with dark fringes. So to have a much elaborate understanding on this, basically this is the wave front of the light. This is a particular phase. And as you can see here, this is the positive and the negative, or you can say that the amplitude of this wave. So when a wave front A and wave front B, they are coming together, they are interfering with each other, what is happening? If you can see here, the positive amplitude of both, they're in sync, so they're in step. So as both are matching, they're syncing with the crest and the trough. what is happening? They are adding to each other. They're adding to it. So resulting is a constructive interface. So constructive interface, what will happen? It will be addition of these two wavelengths. The amplitude will add for wave A and B, and the final wave, which is a summation result wave of A and B, will have the increased amplitude. Okay. Now take for another example, wave A with wave C. Now wave A and C, if you see the crest and the trough matching, they are not in sync. So they are just opposite to each other. What will happen? They will cancel out each other, and the resulting wave of A and C will be a decreased amplitude. You can see here, compared to this two, this is the decrease. Now this particular interactions or interface is called destructive interface. So where the two of the waves are in sync, they come across and they form a constructive interface. And when they are out of sync, they form destructive interface. And this particular interference of the wave fronts is being seen, and they result into formation of bands. So these are the peaks. So basically, if you can imagine like sand dunes, standing on top of a sand dune, this is the crest and this is the trough. So peak and the valley. And based on this, you see wherever there is a destructive interference, you have the valley. Wherever there is a constructive interference, you have the peak coming up and resulting into dark and bright fringes. So this is the barrier. This is first the primary field and then the secondary field, where two slits are open together. And to see, so Young did this experiment just to demonstrate the wave nature of light, but this diffraction phenomena has been capitalized since then to form images. Now, constructive interference occurs when the lines which represent the peaks are crossed together. So the peaks are matching with each other, then you have the constructive interference. Destructive interference occur when the two waves are completely out of phase. As I said, they don't go hand in hand with each other, they are in out of phase, and a peak from one lies halfway between the two peaks from the other, right? So the resultant is a destructive interference. The angle at which the constructive and destructive interference occurs depends on the wavelength and the separation between the sources. So that is important. Okay. So if you can see, this is basically the entire circle of wave fronts which are being created for these two slit sources, and the green and the red, you can see the green one is the destructive interference and red one is the constructive interference being formed. Okay, moving ahead to the final and the last type of interaction, that is the dispersion. So dispersion, if you just recall the refractive part, the refractive index of medium depends on energy of light. Light from higher content of energy, that is the basically, if you see or if you remember the VIBGYOR, violet, indigo, blue, green, yellow, orange, red, the energy associated with violet is the highest. So with linking with that part, so in my first lecture series where I have talked about electromagnetic spectrum, there you can associate the energy associated with this particular colors of wavelength. So if you can recall that light with higher content of energy, so obviously the blue region has higher angle of refraction than light with lower content of energy. So what will happen? The angle of refraction will be higher with from starting from the blue, and gradually the angle will reduce if we move towards the red. And that is why we see a dispersion. So this is basically a white light coming onto a prism, and from this glass prism we have the first, this is the surface from air to glass, and then you have the first diffraction, and then you have again from glass to air, another diffraction is being taking place, and that is why we are getting a dispersed image. So sorry, rather not a dispersed image, but dispersion of the white light. So white light comprises of all the colors of the light, and that is with the help of a prism, you can disperse all the other wavelengths. So this is a small animation. If you can see first for the red, for orange, green, and blue, the maximum angle of refraction or the angle of a deviation of the refracted light path is taking place from the blue, and the blue is associated with the higher energy, right? So with this, so this phenomenon of light interacting with different types of media is being capitalized in microscopy. How we are doing it? When we do, we use several type of detectors. I'll be talking about the detectors used in microscopes. So in this type of detectors, what happened? You need to do some spectral imaging. So for that type, when you want to disperse your light, you have to use a glass prism to disperse your single light, that is maybe a white light source or a metal halide light source, and that light source is passed through the prism and it's dispersed into all the wavelengths. So you can use this phenomenon of dispersion to selectively select, making a selection and isolating a particular wavelength or particular color of light, right? So these phenomena are used in all the lenses. This phenomena of reflection, of refraction, of dispersion, diffractions, they're all being used and capitalized in our favor to achieve better form of images, and how we can get rid of several type of aberrations. So in my next lecture series, I'll be talking about different types of aberrations which we always occur, and how to get rid of those aberrations happening with it.